Bismillahirrahmanirrahim. Math 327, Function Analysis. My name is Dr. Talat Nazir. I obtained my PhD degree in Functional Analysis from the Lahore University of Management Sciences, LUMS. So I would like to teach you this course. It's an excellent course with the various contents which are very important now. So in this course, in the first lesson, we shall discuss about the vector spaces and the norm spaces. Normally, whenever we discuss the courses of sciences, especially in this course, we are focused with the functional equations. Like the functional analysis, we involve some functions and solve the functional equations. Various problems of practical natures arises in physics, chemistry, biology can be solved by applying mathematical tools. So need to employ some function and need to solve this by implying the mathematical way that you have the different tools, different procedures, different algorithms whenever we apply and need to obtain the solutions of such problems. Like in mathematics, normally we solve the different kind of equations by applying some algebraic equations. We know that how to employ the algebraic variables, let x equal to this, y equal to this, and then multiply, subtraction, addition. We have the different tools of mathematics we can employ. But the functional analysis is something different, that you need to employ some functions to obtain the solution of such problems. So first of all, we require some set. For instance, whenever we drive our problem, so basically something in our hand, some set. So what about the set? As you know that the set is a collection of well-defined and distinct objects. Well-defined and distinct mean the elements are unique and they are well-defined. So for instance, the set of natural numbers, the set of real numbers, the set of integers. So different kind of sets we have. The set of students in a class. So the various kind of sets whenever we have, sometimes the sets are finite, sometimes the sets are infinite, so they have the different aspects of that sets. So we need to apply some procedure on that sets. So for instance, we have some function which is from one set to another set. So it's important that you must have some domain, some range, and the mapping or some function. Mapping, I just explained you next that what is about mapping. Mapping is normally the general function. Suppose that you employ some transformation from one space to another space. So this is a mapping. But the function is like from a set to another set, which may be the set of real numbers, set of complex numbers. Here we have the different sets. So after describing the sets, we must be asked about the space. So space normally today, like the contents of our lectures are the vector spaces, norm spaces. There are some examples, some applications we shall discuss about later. But first of all, this about the space. You know, like I described you about the sets, that the collection of well-defined and distinct objects. But space is something more than that set. Every space is a set. But space is how general? Space means whenever you have the two elements, then if you add these two elements, then their sum must be belonging to that set. Okay, so for instance, you have a set of natural numbers. We know that if we add the two natural numbers, then their summation is also belong to that. Their composition is also belong to that. So if such kind of property satisfied some set, so we say that it's a space. Normally, every set is not space. For example, if we take a set from 1 to 10, and look, whenever we add the two elements, like we know that 5 and 7 belong to that set, which are from 1 to 10. Now, whenever we add the 5 and 7, the answer is 12. But 12 doesn't belong to that set. So it means this is not the space, but it's a set. And we know that every space is a set. And now we discuss about today the vector space of this course. Actually, we first of all built some spaces. Some spaces in this course: Hilbert space, Banach space, and the topological vector space, norm spaces. And then we shall able to discuss that how we employ the functions and get the solutions of such problems. Normally we just describe the functional equations later, but on that set we must know that how we can employ the functions and get the solutions. For this, first of all, we describe about the functions. And functional analysis, actually it's a abstract branch of mathematics that deal with the equations of solutions. Many problems and their applications, such as problems related to the differential equations, ordinary differential equation or partial differential equation, numerical analysis, calculus of variations, approximation theory, integral equations, and so many other equations. Their applications and solutions of such problems deal with this course. Normally, in calculus, whenever we face the problems of limits, we deal with the other problems of convergence. So sometimes we are facing with finite, we are in a finite space. For instance, the R is a one-dimensional, so it's a finite dimensional space. Rn is also a finite dimensional space, but it's not always in sciences. Mostly we deal with infinite dimension space. Infinite dimension space mean R infinity, LP space, Lebesgue measurable space, and the more general spaces we need to work on that. The space of functions, the space of bounded sequences, many kind of spaces we are facing. So in this time we are focused on the vector space. So vector space, we need to describe about before we are describing, just I mentioned you that the introductory to the book, textbook is better for you is the Krasik book. By the name of book is Introductory Functional Analysis with Applications. It's a suitable book, and I hope that you really enjoy whenever you read this book and also solve particular examples and the problems of this book. So now we shall study the vector space. So the vector space, for describing vector space, must we have some field. Field may be space of real number, the set R, also maybe some complex numbers. More generally we say it's a field. Normally in our course we take it's R, it's the space of all real numbers. You know that real numbers is a collection of rational and irrational numbers, which you already study in your elementary classes, in the previous classes. Now a vector space over a field K mean maybe it's a real number or complex number, is a set together with the two functions. Here we must have the two functions. First one is the addition function, addition of vectors, that mean K plus is the mapping from x cross x to x is called a vector addition, and dot is a scalar multiplication. Normally with scalar multiply with set x goes to x is called scalar multiplication that satisfies the following 8 properties. So here we know that K I just described that K may be some R or real numbers or complex numbers, and somehow field in the field extension sometimes it's R square, sometimes it's R cube, but in this case we mostly focus on the real numbers, which are I think precisely easy to understand. So what the following 8 characteristics, if some some space satisfy, then we say that it's vector space. The first one is that for all 3 elements x1, x2, x3 belongs to this capital set X, we must have the associative law of addition. That's mean x1 plus x2 plus x3 is equal to the x1 plus x2 and then plus x3. Secondly, V2, that is there exists at least one element denoted by 0, that is sometimes called 0 vector, such that for all x belongs to the x plus 0 is equal to the 0 plus x, and the answer is equal to the x. Note that here the 0 vector, or sometimes called null vector, is a vector whenever we are adding we obtain nothing. In R we know that identity is the element. Whenever we add in any number, then it remains same. We shall discuss about the characteristics of R in this vector space, but first of all we describe the other remaining conditions for the space that must be a vector space. So the third one property of the vector space is that whenever you pick any number x from that set and there exists an element denoted by minus x, minus x mean sometimes it's called the called additive inverse. The additive inverse of each element must be belong to that set. That is, whenever you add x with minus of x, you will obtain the same as minus of x plus x, and the conclusion is 0, mean you obtain a 0 vector or null vector. So it's mean that the inverse of each element must be contained in that set, and that the inverse of each element of that space must be contained in that space. The fourth property is that if you find any two elements in some space, then you must have x1 plus x2 equal to x2 plus x1, and definitely it's a commutative law of addition. Mean vector space must be have this property. And the fifth property is that for all the elements of that space, you must have, whenever you multiply with 1, so 1 dot x equal to the x. We know that the dot operator is a k cross x to x, mean first of all you must have k, mean normal, the element of R. You know R1 is the element of R, so 1 multiply with x is equal to the x. And the sixth characteristics of the vector space is that for all x belongs to x and all alpha beta belongs to the field k, alpha dot beta dot x is equal to alpha beta dot x. So they are the important properties. So here we find that something is obvious or something is difficult to explain, but it's not. Whenever we finish all this, we see that how they are important, how we can specify that here something holds, something not. And now the seventh property is that for all x belongs to the x and the alpha beta belongs to the k, we must have alpha plus beta dot x is same as alpha dot x plus beta dot x. It's a distributive law of addition over multiplication, where addition with scalar and the multiplication with vector. And V8 is that for all x1, x2 belongs to the x, and for all alpha belongs to the field k, alpha dot x1 plus x2 is equal to the alpha dot x1 plus alpha dot x2. It's like a left distributive law of multiplication over addition. Addition in vectors, but the multiplication in scalar multiplication. So here if some space satisfies these all 8 axioms, so we say that it's a vector space. There are the many spaces which are vector space, and there are the many spaces which are not vector space. So they have, every vector space have some important characteristics. We shall later describe about some spaces, those are vector spaces and those are not. But in how we know that the vector spaces and then subspaces, like a space, whenever there's sum of the two elements belongs to that, every scalar multiply with the element of that space must be contained in that space. If some property are satisfied, we say that it's a space and subspace. If their parent space is a vector space, and if the alpha 1 plus alpha 1x plus alpha 2y belongs to the that space, we say that it's a subspace. For all xy belongs to that space. Okay, so it's a subspace, mean like we are familiar with the concept of set and subset. So subset is a particular case of set, mean all those elements that are contained in some particular set, we say that it's a subset. So similarly, the spaces and subspaces have the idea, and it's some generalization which are obtained from the sets. Now the next is, we discuss some examples about the vector spaces. So the very first example of vector spaces is the R. R is a vector space over the field itself. Over the field R, mean you take all the constants that are must be belonging to that, with vectors addition being a usual addition of real numbers and scalar multiplication being the usual multiplication of real numbers. We know that the sum of two real numbers is a real number, the product of two real numbers is a real number. So you can satisfy the all 8 axioms of the real numbers, these of the real numbers, they all satisfies the all properties of vector space. So the space of real R, it's a vector space. R is a vector space because it satisfies the all axioms of all these axioms of vector space. Now the next one is Rn is a vector space. Rn is a vector space over R. Since in the first example we say that R is a vector space, but it's a one-dimensional vector space. Rn is a nth dimensional vector space over the field R with addition and scalar multiplication. Whenever we add the two vectors, we know that we just write into the column form, first vector, second vector in a column form. Whenever the two vectors belongs to the Rn, then we know their additions. The addition of the first vector plus second vector is equal to their component wise addition, mean x1 is added in the y1, x2 is added into the y2, up to so on, and xn is added into the yn. In this way we add we get the addition of two vectors. Under this operation, mean addition, we use this this way. And if we have some scalar alpha, how we multiply with some vector of Rn? So we have alpha times x1, x2 up to xn is equal to the alpha times x1, alpha times x2 up to so on, alpha times xn. Mean alpha multiplied with every element of that vector. Every element mean every of its component, mean it's a n tuple. R is an n tuple, mean it's have the n tuple. So every element must be multiplied with the value of alpha. So whenever we have this addition operator and this scalar multiplication operator, then it is easy to show that the all 8 axioms of vector spaces must be satisfied by Rn. So we say that Rn is a vector space. Normally we know that it's a finite dimensional, so n, where n is some finite number, so Rn is also the n dimensional or finite dimensional vector space. Now we discuss about some infinite dimensional spaces. So the first one, the space of sequence, L infinity. L infinity is the space of all bounded sequences. Bounded means we have how the bounded, you know, when the all terms of sequence, sequence is the collection of elements. So whenever it's every element is bounded by some number, then we say that it's a bounded sequence. For instance, you say that the mod of xn, whenever you pick the entries of R real numbers, so the mod of xn is less than or equal to some m, mean you have some number m such that the mod of xn is less than m, where m is some finite number, then we say that it's a bounded sequence. Another property of bounded sequence that is that it must have its least upper bound and greatest lower bound, mean all values are bounded. For example, the trivial example of bounded function is 1 over n. As we know that 1 over n, its supremum is 1 and its infimum is 0. 1 over n, the first term is 1, second term is 1 over 2, third term is 1 over 3, 4, and it converges to 0. So it's a bounded sequence because its values are in between 0 and 1. So the collection of all bounded sequences in a space is denoted by L infinity, and this space is also a vector space by applying the concept of over some field K, mean you can take any scalar which may be a complex number or real number. So under the following two additions and scalar multiplication defined as follows, that the sequence xn plus sequence yn is equal to the sequence xn plus yn. We know that the sum of two sequences is a sequence. So here whenever you add the two sequences, you know the first term of the sequence is added into the first term, second term is added into the second term, up to so on. In this way we obtain a new sequence, like xn is a sequence, yn is a sequence, then their sum is a zn sequence, where zn is the xi plus yi, where I belongs to the set of natural numbers. Mean for all sequences you take from L infinity, in this way you obtain the addition. And how to obtain the scalar multiplication? Alpha times xn is equal to the alpha xn, mean every element of sequence must be multiplied with the alpha. So in this way we have the scalar multiplication. Under these two operations, additions and scalar multiplication, one can easily show that the all 8 axioms of vector spaces are satisfied, and hence L infinity is a vector space. Now the next one is the space of functions C close AB interval. So it's a collection of all continuous, a space of all continuous functions from defined on closed interval AB, where A is strictly less than B. So the space of all continuous functions is also a vector space, having the operation that if you pick the two continuous functions defined on closed set AB, then their addition is also belongs to the collection of all continuous sets from AB. We know that the sum of two continuous functions is a continuous function. The product of two continuous functions is a continuous functions. It's the continuous functions properties which we studied in the calculus courses. Now in this level, whenever we defined the two operations, first one is addition and second one is scalar multiplication. If f plus g of x is equal to the f of x plus g of x for all x belongs to the closed interval AB, then in this way we applying the addition, because the sum of two functions is a function. In this way we apply the additions, and for any alpha belongs to the field K and f belongs to the collection of all continuous functions defined on AB closed interval, then we know that alpha f also belongs to the C of AB, is a space, because alpha of f is also a continuous functions where alpha is any scalar. So we define the operation that alpha times f of x is equal to the alpha f of x, mean alpha is multiplied with the each term of f for all x belongs to the AB closed interval. If we employ these two operators, addition operator and scalar multiplication, then we can show that the all axioms of vector space are satisfied. Here I must show you a point about the proving that if you will take some continuous functions and give some examples. So this is only the example. Examples are good for understanding, but examples are not useful for proving something. For instance, here you know space of all continuous functions. There are infinitely many functions which are continuous. But if we show some functions which are vector space, but maybe there exist some functions which are not continuous. So for this we must be proved analytically, and for the analytic proof we must have a thing that we must take some arbitrary elements from that space and then we show. Okay, for this we have later we practice about such kind of things. Now here since we saw some finite dimensional spaces, some infinite dimensional spaces which are the vector spaces, some are not. So now someone asks you that give some example that are not the vector spaces. So you can construct many examples which are not vector space. Have you in mind? I give you some times that you can think about it. So there are the many ways. For example, here I would like to drive an example for you that how you can obtain some counter example. So we know that Rn is a vector space for any n. R square, R cube is a vector space, R3 is R4 is a vector space. They all are vector spaces, but many of them are not vector spaces. For example, if we take some subset of the vector space, for example, like I show you. So here if we take some set S, that is a subset of R square. So S contains the collection of elements of R square. Which kind of elements? The collection of all elements which have the property that x1, whenever we add x1 plus we say that suppose x1 comma x1 comma y1, it's the element. We know it's the first element. If we add with the another element, that is x2 or y2. Whenever we add these two elements, we obtain x1 plus x2 comma the y1 plus y2. As you know that it's the obvious way that how we adding the two vectors, like the first component must be added into the first, second component added into the second component. So this is the addition operation. And also how the scalar multiplication we define alpha dot x comma y is equal to the alpha of x comma y. So it's the collection of all those sets which have the property that if you add the two vectors of that, so their sum is equal to the x1 plus x2 comma y1 plus y2, and whenever you alpha multiply with any vector, then it's multiply with the only first component, not with second component. This is the addition way. Now this is a scalar addition way and scalar multiplication whenever we define some set. Now let us see that is this S is a vector space. So we know that for counterexample we must be check that is this satisfy every property or not. So for this we can see that, okay, what about the V7? Note that V7 property which we already defined, that we have for any two scalars alpha plus beta of the scalars which are alpha plus beta times the x, it must be have the alpha x plus the beta x for all x belongs to the set V, where V is a vector space. If here in the V we say that this V equal to the S. Okay, let us check that it satisfies this property or not. We know that if any one is not satisfied, then such a space is not a vector space. So for this, look, if we take the first side, for example here we have alpha plus beta. If we multiply with some vector that is x comma y, which is equal to the alpha x and the only y we have, this one can say it's equation number 1. And on the other hand, the right hand side of this, what about the alpha x comma y plus the beta of x comma y. Here the x comma y are the elements of S which is contained in R square. So we know that, so by applying the characteristics of set, how we multiply the scalar multiplication, so this will gives us the alpha x or y, and from the second one here we have plus the beta x of y. And you know that how we can define the addition here, like in above, we know that we obtain alpha x plus the beta x comma the y plus y, that is, and which is equal to the alpha plus the beta of x or 2y, which is equation number 2. Now from equation number 1 and equation number 2, we know that in V7 the left hand side equal to the right hand side, but here note that is the one side is equal to the right hand side, here you have the only one y and here you have the 2y, so it's counter that case. So it makes contradiction, since the equation of 1 is not equal to the equation of 2, so it's not a vector space. So it means that if we define set S in R square such as the addition of the two vectors, the element of R square is same as the usual addition, and the scalar multiplication is that alpha x of y is equal to the alpha x of x comma y. So alpha is only multiplied with the first, then it's not a vector space. Similarly, if you take the alpha with multiply of alpha with only the second entry, then you can show that it's again not a vector space. And also for the addition, you can some changing, like x1, this is the way that I tell you how you can construct the counter examples. For example, in here x1 comma y1 plus x2 comma y2, if we have to take this one is only x1 comma y1 plus y2, then we can see that some of the properties of vector spaces are not satisfied. If we found that any one of property is not satisfied, then it's not a vector space. So for the vector space, the all conditions must be satisfied. Here something for your thinking, that if we take this alpha of x over y defined here above, if we take this equal to the alpha x comma 0, so in this way we define, then my question is that, is this a vector space? The answer is yes, because now you can satisfy the all conditions. Look at the above. Here if you have the 2y, in place of 2y, if y is 0, so 2 multiplied by 0 is 0. So, and also in the equation number 1, the y equal to 0. So from first equation and the second equations are one of the same thing. So it's mean V7 is satisfied. Similarly, the other conditions can be satisfied, and hence we can say that it's a vector space. Okay, so in this way you can construct some spaces which are vector spaces and some spaces which are not the vector spaces. Now we move on the next, that is norm spaces, very important spaces. Norm spaces mostly we discuss for convergence of the spaces. For instance, in calculus we have different problems regarding the limiting process, convergence, approximations, continuity, derivations, this kind of things we are facing in our vector spaces. Now we need the notation for the distance. In R we know that the distance from closed interval AB is the B minus A. But someone asks you that what is the distance between two vectors? What is the absolute distance between the two elements of R squares? What is not on? We know that the vector spaces may be a finite dimensional, sometimes infinite dimensional spaces. So how you can measure the distance between them? And whenever we are discussing about the distance, we study about the shortest distance. Okay, here we discuss about the shortest distance. So for this we provided the notion of norms. So the definition of a norm space is, so if a function from any non-empty set X to the set of non-negative real numbers satisfies the three properties n1, n2, n3, then we say that it's a norm space. What properties? The first property is that it must have positive definiteness, means for all the element of that the norm of X must be non-negative, and if X belongs to that which norm equal to 0, then this element must have 0. This vector is equal to the 0 if its norm is 0, and if the norm is 0, then vector equal to the 0. That is if and only if case both must be satisfied in both hands, and it must satisfy on the both hands. Now positivity definiteness will also show from the definition of this, mean it's a function from X to the set of non-negative real numbers. So since non-negative real numbers, your range set is from 0 to infinity, so there is no chance that you obtain the negative elements. So also the second characteristics of norm space is that for all alpha belongs to the set R, respectively, you can take some complex, the collection of complex numbers, any field, and then you have for all X belongs to the X, the norm of alpha x is equal to the mod of x times the norm of x. Here, if your alpha is positive, we know that the mod value of alpha is equal to alpha if alpha is positive, and if alpha is negative, then the mod of alpha is again makes the positive element, that is the minus term alpha, which is the property of mod. Just I write here that the mod of x is equal to x if x is positive, and the mod of x is minus x if x is negative. Positive, or you say that it's non-negative. For the non-negative, the values remain same because the mod of 0 is 0, but the mod of minus 7 is minus times mod of 7, which makes plus 7. Minus times minus makes plus. So if these properties are satisfied for if these properties are satisfied, then we say that it's a second characteristics of norm space. And the third one is that triangular inequality, mean the norm of x plus y is less than or equal to the norm of x plus norm of y for all x, y belongs to that set x. So n1, n2, n3, if any of the space having these three properties, then this space is a norm space. I hope that these three properties must be you take on your fingertips, because these are the tools which are very important to check the things, and literally we build these spaces. Then we shall see that how we apply some functions and some operations to that employ the things from one spaces to another spaces, and what's their characteristics and how they are useful to approximate, useful to get the solutions, used to converge to the answers or solutions. So in a space, if we impose this function which is norm function from this non-empty set x to this 0 infinity, then this space is called norm space, and this function is called norm on that set. For a non-empty set with having this norm which have these all three characteristics is called norm space. We say that x comma norm is a norm space. So a norm space is a vector space x equipped with a norm. Your norm space is normally a vector space equipped with norm which you can define in various ways. So also, if you have the two elements, then their norm of x minus y provides the notion of closeness, the notion of closer distance, the notion of their that how they are close to each other, close to each other. That is the distance or shortest distance between the 2 points. And also, you know the distance from origin. Normally the norm of x means it's the distance from the origin or from the 0 vectors is the x minus 1, x minus 0 norm. So in this way we can calculate the distance. So the norm generalizes the distance of the two vectors. We know that in R how we get the distance, but norm is actually the generalization of R, because what about the distance in R square? What about the distance in two functions? What about the distance in vector spaces? Distance between the two vectors. We need some extension. So norms will cover all these cases, that how whenever you are facing with some set, then you can define some norm on that, and you can calculate the distance between their elements. Literally we describe the metric space and see that how the norms and metrics will be merged together and some of their beautiful characteristics. Now we discuss some examples on norm spaces. The very first example of norm is on vector spaces. If you have the R, which is a vector space we saw previously, and if we define a norm on that is that the norm of x is equal to the mod of x for all x belongs to the set of real numbers. If we take the mod of x, so the mod satisfies n1, n2, n3, these three properties of the norm spaces, and hence we conclude that the mod function is a norm space because it satisfies all three axioms, because the mod of x is greater than or equal to x for all x. Also the triangular inequality is holded into the mod function, and similarly the third one, that the mod of every value is positive. The mod of alpha x mean alpha times x, whenever alpha is real number, x is real number, so the mod of those is equal to the alpha mod and x mod, which is equal to the alpha multiply with x. So in this way one can show that all three properties are satisfied and R is a vector space. The second example is about Rn, which is a vector space. Rn, we know that Rn is a finite dimensional vector spaces if we define a norm, sometimes called norm 2, that is some norm where the value p equal to the 2. How? It's norm 2 of x is equal to the summation of I from 1 to n xi mod square, and taking the whole square root, where x is a vector in Rn. It's an n-dimensional vector in Rn. So in this way, whenever you define the norm, sometimes it's called the norm 2. Okay, there are the many norms on Rn, so then Rn is a norm space because this norm satisfies all three axioms n1, n2, n3. So this is the norm 2, but the question arises in our mind that is there another way you can define a norm on Rn? The answer is yes. But one thing is that here you have n is a natural number, so it will cover all n's, for example n2, n3, n4, so all of Rn's are the vector spaces where n belongs to the set of natural numbers. So how we can construct the different norms on this Rn? So for example, if we take norm 1 where p equal to 1, p is some power, like look in the previous example, here the 2 means you will take the p here and here you take 1 over p, so it's number p where p is some natural number. P2 mean the power 2. Here if you take just p equal to the 1 in that case, so it's equal to the summation from I equal to the 1 to n xi mod. So the sum of all values, all positive values of that vectors, all these components, whenever you add you will take it's the norm 1. And also you can define another norm that is called the norm infinity. It will take the max value of that, the max value of positive maximum value of all components of that vector. In this way you define the second norm where x is equal to the x1, x2 up to the xn. It's an n-tuple element contained in Rn. So these are also the norms because these norms satisfies the conditions n1, n2, n3, which are the important properties of norm spaces. So we say that here Rn and the norm 2, similarly Rn and norm 1, Rn and norm infinities, these are the different norm spaces. One thing about here that these are very important norms which are required for the various purposes. Whenever we find the shortest distance, we find the length, each one will give us the different approaches, and these are the important things that we can construct some examples, sometimes construct counter examples. In this course you also will see that how you can construct the different distances which are useful and helpful to analyze the different spaces of functions. Now this illustrates the important fact that norm of a given vector, we can obtain various norm spaces by choosing the different norms. You can also construct some different norms. Sometime you can take the square root of the absolute of first value plus the square root of absolute of second value, and in this way for the case whenever you are picking only the non-negative real numbers. And the other ideas can be considered for constructing norms and for their examples, properties, and whenever we imposing some functions for solving some functional equations, then we see that how it's useful and how it's effective. So these norms depends on particular applications at the hand. We can construct different kind of example, different kinds of distances, and different analyzations of the things by applying these norms. For example, here if we suppose that we are interested to comparing the economics preferences of the countries by year to year, mean in every year we have the 365 days. So for this we obtain a 365 tuple, that is every element is 365 tuple x1, x2 up to the x365, and to record the daily industrial averages. A measure of differences in yearly performance is given below. How we can see that what is the measure of differences? So that is x minus y equal to the summation from I equal to 1 to 365 xi minus yi mod values. Look at there, in this way x1 minus y1 mod plus x2 minus y2 mod plus x3 y minus y3 mod plus up to so on, and then plus x365 minus y365 mod and their summation. If we obtain the summation, then we can obtain the measure of differences yearly in their yearly performances. And also of course it's a norm 1 of R365, mean the dimension of R in this case is the 365, and it's arise naturally. We can analyze economical problem in this way. We also sometimes discuss the yearly by employing their monthly incomes, monthly their weightages. For instance, we record the index for a year by given 12 tuple element. X is the 12th tuple element. A measure of differences in yearly performance of the cost of living index is given by x minus y is the max of xi minus yi, where I is from 1 to the 12. So in this way you obtain the maximum differences, absolute of maximum differences, and then you can analyze that for where you in this function choose the maximum of all that, where the maximum differences occur. In somewhere your values maybe one is negative, another one is positive, you get the maximum difference between that. So in this way you analyze that which month you will see that the maximum difference occur. So it's the R it is an infinity norm, and hence this distance relation is a norm space, and one can say that R12 comma infinity norm is a norm space. For norm space you must have some space where the space is R12 and the norm here you defined is infinity norm. So the various kinds of economics applications, physics, chemistry, biology, we require the norm for measuring the distances. Now some more examples about the norms. So again we discuss about the space of all bounded sequences, L infinity, that is the space of all bounded sequences. Now we see that how this norm shows the impression, how we can construct the norm on L infinity. We define, we saw that L infinity is a norm space because how we can find the sum of two sequences, bounded sequences, each term of sequence is added into the another term of sequence whenever we add the two sequences. Also whenever we multiply scalar alpha with the sum sequence xn, then alpha must be multiplied with the each term of xn. that is we already saw in 1.1 and 1.2. Now we define the infinity norm on this space of bounded sequence, that is L infinity. So for every element of that L infinity space, since every element is a sequence, so the norm of xn, norm infinity, is defined as the supremum of x of mod of xn. Mean you will pick the supremum of the absolute value of that sequence, and you can check that it's a norm space that satisfies the all conditions. Mean L infinity and this norm is a norm space, or you can say that you have a vector space L infinity and you define the L infinity norm on that. So you can have a norm space L infinity, and the norm infinity is a norm space. Another beautiful example, we see that the space of all continuous functions defined on closed interval AB, where A and B are the two real numbers, A is strictly less than B. Now consider the vector space comprising the functions that are continuous on this closed interval AB with addition and scalar multiplication. We already saw earlier that whenever we add the two continuous functions, so how we get the sum of two continuous functions is a continuous function, and whenever you multiply the scalar with some function, then it's multiply with each value of f of x. So look at this diagram that we have the two functions f and g, the set of all continuous functions g whose graph lies between the two dotted lines. These dotted lines are the boundaries, mean they have some epsilon difference from upper and lower sides. So in this way we obtain an open ball having center with f and difference with epsilon. Epsilon is here considered as a radius. So it's collection of all functions g, all continuous functions g, which have the distance is less than epsilon. What about the distance? Here the distance is a norm, and the norm of f minus g must be strictly less than epsilon, where epsilon is some finite positive real number. Now in this way we define the norm infinity, f infinity is the supremum of x belongs to the closed interval AB, is the absolute value of f of x, where f belongs to the closed interval AB. Then this infinity norm is a norm on collection of all continuous functions defined on closed set AB. Similarly, one can describe another norm on that, which is very useful norm, that is called norm 1 of functions, norm 1 of continuous function defined on closed interval, that is the norm of f1. The norm 1 of f is the integral from a to b mod of f of x dx, where f is a continuous function. And you can easily check that this is also a norm that satisfies this condition. So after this we have some problems in our mind that I want to share with you, that how you can solve the things. So there are the many tips, many ways. Whenever you read the textbooks after the lesson, you are able to see the different problems how we can tackle. So for my first here problem, I discussed with you that if you have x with dot norm be a norm space, mean any norm you define on that. For any norm space, you can prove that the absolute value of norm of x minus norm of y mod is less than or equal to the x minus y norm. So look at there, you can apply the properties of mod and norm, you can prove this inequality. And again, one thing must be in your hand, that you know the property of one property over here, that the absolute value of x is less than y. If you have this property, mean this is important characteristics of mod value, where it's a number of r. Look here that the mod of x is some non-negative real number, so we are in r. So for this case, if this happen, then we must have the minus y is less than x is less than the y. Note that here your y is greater than and equal to the mod value of x. So since the mod value of x is either 0 or greater than 0, now since the y is greater than the mod of x, it means that either y is positive or y equal to the 0. There are only the two possibilities on y. Mean its y is either 0 or y is greater than 0, mean y is positive number. And x mod, we know that, what about the x mod? The value of x mod is either plus x or the minus x. Defaultly it's plus x if your x is greater than and equal to the 0. And this is the case if your x is negative. So if you impose these two conditions on this, you can appreciate this property that the norm of x minus y, whenever you take its mod, then it's less than or equal to the x minus y norm. And this is up to you. I hope that you can easily apply these steps, the norm properties and the mod properties. You can prove this identity. And in my second questions, if x belongs to the R, then if you define a norm, x norm is the mod of x square, then is this defined norm is a norm on R? You can think on it and give me some precise answer about this. Mean does it satisfy the all three properties that are the properties of the norm n1? And what about the n1? Since n1 is that the norm of x is always non-negative, mean greater than or equal to the 0 for all x. Look here, the absolute value and their square, so it's clear that the square, if x norm is greater than 0, then definitely its square is also greater than 0, and hence the norm of x is greater than 0. And secondly, if the norm of x is equal to the 0, if and only if x is equal to the 0. Think on this problem. Also for n2, that is the alpha times norm of x is equal to the mod value of alpha with norm of x. This satisfied or not? So for this, just I helped you in there that note that if we have the alpha x norm, just consider this one. This is, so how we describe this one? According to this rule, it makes that it's the alpha, this is the alpha x square, and we know that the mod of alpha x is same as the mod of alpha square and the mod value of x square, but that is not equal to the alpha mod and with the mod of x square, which we have you can note that it's equal to the alpha with this is the norm of x. So since here what we are checking, it's the n2, the property n2. Since n2 is not satisfied, hence this example shows that this example is not the norm space. So you can construct the different kinds of norm, sometimes the square root on that, and there are various ways, various analysis you can apply and get the different situations where the norms occur or not. So the norms will gives you the different ways that how you can get the answers, how you can obtain the difference between two values. Sometimes in projection the norms are important, because from the projection you can obtain the perpendicular distance that makes the shortest distance. In triangular law, in various ways, these norms plays an important role. So after that, it's the Cauchy-Schwarz inequality. I discussed this property with you, that Cauchy-Schwarz inequality. So about this inequality, we have, what this inequality, it's a very important inequality we mostly use for solving the functional equations. That is, if x and y are any two vectors, if these are the two vectors, then what happens? Then we have the x y mod is less than or equal to the norm of x and the norm of y. It's very important property. Look at there, if we have the two vectors, how we can multiply the two vectors? Whenever we multiply the two vectors, then first component of the first vector multiply with the first component of the second vector. Again, the second component of the first vector will add into the second component of second vector, and up to so on. Similarly, for the, if you are in Rn, then it's the nth tuple of first vector will add to the nth tuple of the second vector, and then their addition. And whenever you add the two vectors, you get some real value, and whenever you have the real value, then norm change into the form of mod. So the mod of x y is less than or equal to the norm of x and the norm of y. Sometimes we study this in the way that in some time, how we write this, x norm into the y norm over the norm of x and the norm of y is less than and equal to the 1. Here, if for the condition that if here the norm of x and norm of y's both are not equal to the 0, because we know that the zero division is not allowed. Zero division means whenever you multiply with some zero scalar, then its converges, the values goes to infinity, but infinity is since not the part of R is the interval from our collection of all those values which are in between minus infinity and plus infinity. So in this way you can write this one. And here one thing note importantly, that since the x y mod is equal to the x mod plus y mod, we can write this into the form. And also one can write this Cauchy-Schwarz inequality in this way, that it's actually equal to the x, the mod of x, the mod of y over the norm of x and the norm of y that is less than or equal to 1. Again, you can apply the mod property. You can rewrite this inequality into the form as that the minus 1 is less than and equal to the x mod into y mod over the x norm over y norm. There are the many applications of this property. You know, normally the sine law, cos law, the all values are in between -1 and +1. The cos value also contained in that between. So similarly, the length, distances in the planes, we shall discuss later about that, how these are important, how the Cauchy-Schwarz inequality we can apply for the projections and such kind of applications. So the Cauchy-Schwarz inequalities is very effective and useful in a vector space. Whenever you define some norm, some length, then you can apply and use this property to obtain the solutions of functional equations. So today this lesson we discuss about the norm spaces and vector spaces. We saw that the norm spaces and the vector spaces, their examples, how they are important. In vector spaces we saw that if space satisfies the 8 axioms, V1 to V8, all these conditions of vector spaces, if some space satisfy, then such a particular space is called a vector space. And secondly, about the norm spaces, we saw that if n1, n2, n3 satisfies by some vector space, we say that it's a norm space. And we also saw that the different norms in finite dimensional spaces and infinite dimensional spaces, because mostly we have the problems we are facing with finite dimensional and sometimes infinite dimensional. For both kind of problems and for their solutions, we must be in hand some space to tackle the problems and apply some tools. So for the norm, whenever we define in some space, we obtain a norm space, and there are the many norms. We already discussed that norm 1, norm 2, norm infinity in LP spaces, LP where P is some natural number. When P equal to 2, it's norm 2, P equal to 1, norm 1, P is infinity, that is a subnorm. Also in a functions, the space of function, we have the subnorm as well as the norm from the closed interval a to b, integral value of a to b, then mod value of f of x dx. In this way we construct different norms. Also we saw that which spaces are not norm spaces, and we define some norms and see that how some spaces are norm spaces and some spaces are not the norm spaces. Analytically we must know that how we can prove the things and how we can give some counterexample if we saw that here the conditions, all conditions are not satisfied. And lastly, we saw the Cauchy-Schwarz inequality, that is the important consequence obtained by the norm space, that is for any two real vectors we must have the mod value of x, y is less than or equal to the x norm, y norm. In the next lesson we shall study about the metric space. We shall see that how the metric space are linked with these norm spaces, and also with vectors, how we can construct the different kinds of metric on that and their applications. And then we shall employ some functional equations and their solutions, and Banach spaces, and then Hilbert spaces and their different applications we shall study into the next lesson. If you have any questions about that, I hope that in the next lesson I will cover that of you, and also I am focused in that lesson that nothing remains for you, that you will the things which are back for you, I try my best level that everything will cover in that lessons. Plus I also give you some examples and some exercises related to that later, which are helpful to you to analyze the things. You can follow the different texts, international texts, which are very effective on that, especially the Introductory to the Functional Analysis book by Krasik is a good book, and also you can get any other text, you can employ the things. The materials is somehow equivalent in the various textbooks. So thank you very much for your attention. So next class we will meet and proceed the next things. So Allah Hafiz now.